So today we're going to talk about automating array program partitioning with PartIR. It's a joint project between several people in DeepMind and Google Brain. So a little bit of recap about what is the programming model we target. It's the traditional array programming model where instructions manipulate n-dimensional arrays, and they include operations like dot products or convolutions or pointwise operations. And its origins come from APL, Fortran, MATLAB, that tradition of languages. It's been very popular for numerical computing and deep learning. And the reasons for popularity is maybe naturality for some people or maybe habituality for others, with notable exceptions trying to break out of the paradigm, like DEX, for example. So in this talk, we're going to take the array programming model as given, and we're going to focus on distributing programs written in this model. And there's a bit of an asterisk here because we're going to need information that goes a little bit outside the traditional array programming model. So kind of, yes, array programming model, but a little bit of extra semantic information is going to be needed. So deep learning, which is kind of the area that's kind of close to me, my working environment, brings forth a case for extreme scaling of array programs. Because we know that bigger deep learning models perform better, and therefore, research scientists do try to scale up their models and always come up with need for more memory and more memory and more flops, basically, for what they need to train. So, in fact, for this reason, training on a single accelerator device is kind of a thing of the past. Accelerators typically come in system configurations with custom interconnect networks. For example, Google offers TPU pods, and NVIDIA offers kind of similar pod and superpod designs that involve dozens or hundreds or even thousands of accelerators. So given these researcher needs and the available hardware systems, partitioning is key for A, researcher velocity, and B, for the return on investment on hardware. Yet it remains in terms of practicality, it remains an expensive and challenging task for practitioners. So why is that? Let me just outline in one slide what is the space. How do people try to partition these research workloads to multiple devices? There exist multi-device programming models. For example, in the JAX, JAX is a library for array computations and deep learning. In the JAX model, there exist combinators like PMAP, like parallel map combinators, or just-in-time compilation of a program for an accelerator, instructions for collective communication, or explicit device transfers. And basically, in this model, people just program against multiple devices manually. So programmers are responsible both for performance, but also for the correctness of their code. If they somehow miss a collective operation and all reduce somewhere, the program is just going to be wrong. So that model requires either known sharding strategy, you have to know exactly what you're programming, or expensive rounds of annotation, profiling, try to write the code again, and also may suffer from system level issues, not just semantic correctness. Secondly, there's improvement on that. There's improvement on that, the single device model, where people can write single device programs, and additionally supply some sharding annotations that can drive some compiler passes. So for example, in this programming model, they say, okay, this is my tensor computation. And by the way, I want you to split my parameter 35 into these 4 devices. And there are some compiler passes by the XLA team, for example, that are able to kind of take that information and guide the sharding of the program based on this information. So that's a big deal, because programmers are responsible for performance, not really for correctness anymore. Like, correctness has been handled by the compiler. It can also be expensive in terms of experimentation time to really figure out which one is the correct sharding annotation and what exactly the compiler pass is doing to the program and how they could fix that. But still, it's a substantial step forward. And finally, there's the automated search-based solutions, like FlexFlow is a kind of a well-known library for this, that basically you just give it a single device model, in effect, and it can actually explore a search space automatically of possible let's say, partitions of this model into accelerator systems. So we are also targeting that third aspect here, but our motivation in design has slight differences, and also the mechanics have slight differences. So our setting is partitioning for researchers. So we need to support a fast-paced research program. That means that we need to support a rich set of array programs, which are constrained only by a de facto, really, there's nothing foundational about it, by a de facto set of ND array combinators, like, for example, the ones exposed in XLA. And also, we want to be platform independent. So we do not want to rely on a specific compiler, specific runtime. We want to be retargetable. Then the solution must enable speedy research and development cycle. So basically, we just need to spend a few minutes to a good enough solution. And we want to be able to scale with more resources. For example, if it's going to take 3 or 4 minutes to schedule a distributed training experiment on some cloud infrastructure, we want the time to find the partitioning, to search for a partitioning, to be no more than a few minutes as well. Otherwise, it just becomes like a bit too expensive to iterate. And the scalability of the programs we're targeting here are XLA. HLO is a code name for the high-level operations of XLA, which is really it's really the tensor operations of XLA. It consists, the target is maybe programs of 50,000 to 300,000 instructions, and we want to partition them over 1,000 chips or something like that. And finally, we want to be able to compose with other JAX APIs, and we want to eliminate as much as possible the need to annotate user code with sharding annotations. So let's see how we're going to do that. So I'm going to give you an overview of the system, and then I'm going to focus on some parts that are a bit more relevant for programming languages, maybe audience, which is the internals of the IR that we're using. So on the top left, we see some JAX program. We do some stuff with the devices of the system. We make them viewable as an array of devices, a 2x4 array of devices. And we give them names. We give this array names. We call them batch and model. And then we call this function that we are exposing, which is called automap. This is the user-facing API of PartIR, where we give it a function. So automap is a higher-order function. It accepts a function called the update, which is maybe a training step of the neural network. We give it some information about the mesh and which access of the mesh we are supposed to partition over. And what we get back is another function, the update function on the return, which is now distributed across the devices. And the rest is really just the details. But the way it actually works is that through ordinary JAX tracing facilities, an XLA program, an XLA tensor program, is traced out of the original update function. So from Python, we go to XLA. XLA is ingested into our own IR, which we call PartIR. And there is a rewrite engine that is driving transformations in PartIR. PartIR gets lowered to another IR, which we call PartIR SPMD, which is more suitable for expressing SPMD-style computations, like parallel computation over devices. And that is the level of the stack in which we do simulation and static analysis to feed back that cost back to the rewrite engine that will drive transformations in PartIR. So I'm going to go in more detail about how these rewrites happen and these transformations. But this is the general overview of the system. When we are happy, we materialize the PartIR SPMD program as another XLA program, but suitable for running in an SPMD fashion with suitable collective operations inside. And that goes to the TPU or GPU runtime. So this is the general overview of the system. Now I'm going to tell you a little bit more about what is PartIR and what is PartIR SPMD. What exactly are these languages? So on the left, PartIR is an MLIR. So MLIR, for those who do not know about it, is a project, is a compiler framework allowing multiple dialects, languages, they call them dialects in that terminology, to be defined in terms of their semantics, in terms of their verification, and coexist in the same compiler framework. So PartIR is another dialect, MLIR dialect, which is layered on top of a pre-existing array dialect and its compiler really, and its runtime. So MLIR includes statically shaped array types. These are shared with the underlying array dialect. It includes iteration and reduction constructs, loops of some form. I'm going to get back to that in a second. And it also includes some rewrite rules for manipulating these iteration, these loops, basically. So it really has nothing to do with partitioning at that point of abstraction. It's really the tensor operations of the underlying language, and some extra iteration-like constructs of PartIR native iteration constructs. And there are some close relatives to the concepts of iteration loops that we're going to see here. Dex or Linalg, which is another MLIR dialect, or F-smooth, experiment with similar ideas. Now, this is what PartIR is. What PartIR SPMD is, it's a language, as I said, that does not have any of these iteration constructs. It also does not have array operations. It relies on the underlying language array operations. It rather has types that express redistribution and replication of data on multiple devices. So a type can inform whether how exactly a value is partitioned on multiple devices, or even replicated, or combinations of these things. It also includes explicit redistribution instructions. It includes explicit SPMD ops, which are basically little kernels or regions, as they're called in the MLIR terminology, that are supposed to run in parallel on all of the devices of the system. So at that level of abstraction, it's actually easy to reason about the cost, because all the data transfers have been manifested as explicit instructions. Whereas that's not the case in PartIR, which is really just loops. So that's kind of the system. So I'm going to go into explaining the PartIR basics and its rewrite system. And for this part of the talk, we're going to ignore the meshes and the devices, the stuff that I talked to you before. We're going to return to it towards the end of this section, because that part is not relevant for the foundations, for the theory of this. So PartIR has really a few constructs. It has range values. When we say we have a range type, range of n, which simply denotes the set 0 to n minus 1. So in programming languages, we'd call this a finite of n, really. So we use range values to slice, basically. So we have a slice op that can take a statically known dimension index, an array typed value x, and the actual range value. So for example, the example on the right is informative. If I see x of type 64 by 32 by 64 float 32s, and I see r range of 4, then I can slice on the 0 dimension, and I'm going to get a tensor of where the first dimension is now 64 by 4, i.e. 16 wide. Or I can slice, for example, on the second dimension, dimension 2, and I'm going to get a tensor which is 64 by 32 by 16. So pretty straightforward so far. And we're going to assume that the ranges divide the dimensions when we're going to use them. So this is going to be part of the well-foundedness checks of the language. We have some extensions about what happens when this is not the case. But for this talk, let's focus on everything divides perfectly. Okay, so constructs number 2. Now this is the most interesting really construct of the language. It's a higher order loop-like expression, which we call the tile loop, which takes a statically known dimension, and it takes something like a closure. In MLIR terms, closures are called regions, really. And so you can think of this as a closure that takes an argument r, which is a range, and gives you back some expression. And now, how do we type this? So we type the expression, the body of the loop, as giving you a tensor of size, where in the relevant dimension 1 here, the size is n over k, if the return of the whole expression, y, the type of the whole expression, is a size n. So you can think of it as some sort of loop that's giving you the chunks of the array one at a time, along the dimension that you care about. And you're kind of implicitly stacking them all back together. So for example, a very naive reference semantics for this implementation is exactly this. I'm going to run all of the loop iterations one by one, and I'm going to stack on dimension one all the chunks. So, right, let me continue. So there's another op which is a little bit like that, which is just a reduction. And in fact, it's a reduction with just a summation, just an add. It's not a generic semiring. So we are here. We have a loop again, and the loop is returning chunks of a specific size. And all we're doing is simply summing, adding up all these chunks together. And notice that there is no type change between the body of the loop and the return of the loop. So you can see how a sequential semantics for this could look like. You just compute all the chunks individually, and then finally you just sum them all together. Or you can also start seeing how this could be implemented in a distributed setting, where you have every device operating on a specific iteration of the loop, and in the end, all the devices perform a collective all-reduce communication, where they just sum and get the result of the reduction. Okay, that's it really. I mean, this is literally what PartIR is. So where it becomes interesting is in what kind of equational reasoning does this language allow us? And now this is a little bit where we're going to go out of the traditional array programming model. We're going to enrich that with a little bit more semantic information, really. So what happens is that every tensor op in the underlying dialect is registered. So we have a little database where we register the underlying tensor ops with information describing really the equivalences of this op with respect to tiling or reduction loops. So for example, if I see, so let's think of a familiar matrix multiplication. So where we have x of type n times m and y of type m times o. What kind of equalities hold for this matrix multiplication? Well, we know that if we try to multiply x and y, that's equivalent to doing smaller multiplications with slices of the first input along the 0 dimension, and then stacking them all back together. This is the first equation I have up there. The second equation says, well, you could do the same thing if you just multiply the first argument in its entirety with slices of the second argument, and then all you need to do is you need to stack up all of the results on dimension 1. And then finally, there's a third equation that says, well, you could also take slices of the first and slices of the second on the reduction dimension, which for x is dimension 1 and for y is dimension 0. And all you can do, and afterwards, is just sum them all up together. And that's also a valid equation. So we have a little data structure that expresses this concisely in our implementation. The details of that data structure are not particularly important. But I want to say that yes, this data structure really encodes information that's not present in the at least naive array programming model. So if I just say matrix multiplication, the type of matrix multiplication, I have no idea which one is a reduction dimension, which one is parallel dimension. How should these things propagate through? What do we do about that? So we, as I said, we register all the array ops of the underlying language, or as many as we can, with our registry, which is generally easy and intuitive, but it can get really, really hairy. So as an example, if you ever happen to browse on the XLA scatter op specification, you'll figure out that it has, I don't know, like 9 operands. Out of them, I don't know, 6 or 7 are statically known, and they affect what kind of axioms could be derived for the scatter op. And I have to make the embarrassing statement that in the absence of a formal specification of some of these ops, for the most hairy ones like scatter, we actually have tests to guarantee that our registration is correct. So this is a little bit of a call to this community for more formal specification of these things and having ways to reflect some of that stuff a little bit better. Okay, so rewriting. So now we know the equivalences, right? But I haven't told you anything about how do we do any sort of rewriting. So the first kind of rewriting that we do, we call them dumb tiling actions. And we call them dumb tiling because they have nothing intelligent about them. They're really dumb. They are really serve as bootstrapping the whole rewriting process. So if I see an SSA value or a value X, and I can always rewrite it as a tile along a dimension, where inside the loop, I can slice on the existing dimension. So basically it says a tensor is really equal to the concatenation of chunks of slices of this tensor on the same dimension. I don't know why I have two examples here. I think one would be enough, but they do not demonstrate something different. So it's a pretty simple rewrite. So we can control that through an action. So our search agent, one of the basic things that's going to try is this specific action. It's going to bootstrap the whole process. So now some more interesting things start happening. So here's an example where, so we call these propagation rules, and they really have to do with the consequences of introducing these tile loops. So here we see an example where we have X, it is defined as a tile loop, and we see that X is used inside a matrix multiplication loop. So at this point, we can trigger the equivalence for the matrix multiplication loop, and we can say, aha, okay, let me try to rewrite the matrix multiplication loop so that it operates on slice, so it becomes a loop that operates on slices of the original input. The second rule is kind of the similar for y when actually when y is tiled. There is a small typo in this slide. And the third rule is when x and y are tiled on the reduction dimension. So basically, these equivalences that I mentioned before are triggered by the presence of some extra tiling information in some of the arguments of the ops. Then there's another form of propagation which is pushing backward. So it's kind of a dual thing. Here we have a definition, which is one of these ops, and its used is sliced. So in that case, we may want to rewrite the definition as a tile. Why do we want to do that? We want to do that because likely the context C in which the slice occurs is a loop, is a loop, and that would fuse later on with the loop that we insert right now in the definition. So this is the second rule of propagation. And then we see here there's a kind of a more exotic form of propagation, which is if we see a matrix multiplication operation, for example, where one of the arguments is tiled on one dimension, then we can look in our registry and say, wouldn't it be really wonderful if the second operand was tiled on the 0 dimension? Because then we could create a loop for it. So in that case, that's what we do. We create a tiling of the other operand in case some operands or results are tiled or kind of sliced. So we call this inference. Let me see. I don't know about this. So apologies for the sound problem. So actually, and now we get back. Now we get to the most important rule of all of the system, which is fusion, basically. So it happens once a tile definition meets a slice use, and I put an asterisk there saying, and we are allowed to inline because it's actually a more complicated question about inlining, for example, if the operand is used multiple times, etc., etc. But in terms of foundations, again, we see a tile definition and we see a slice use. And what happens is that the slice use, we replace the slice use with the body of the tiling loop appropriately renaming the corresponding range value. So this is a little bit like a beta reduction, or it's a little bit like you can see the same concepts in the DEX paper or in FSmooth. So in other words, there's an introduction and elimination form for tile and slice, and they kind of fuse together. So this is the reason why we've been inserting all these extra tile loops to enable this fusion to kick in later on. Okay, so that kind of concludes the description of the rewrite system that I had. I wanted to spend a few minutes to go back to this device meshes business. So one may wonder, okay, how are we going to actually lower and execute PartIR programs? There's nothing about distribution here so far. And indeed, we have option one. We can create serial loops, as I mentioned, which could be useful actually. Some machine learning needs require sometimes creating sequential smaller loops, because that could reduce peak memory. Option two is lower to some form of fork join parallelism, for example, on multi-core machines. But we're interested in option three, which is SPMD parallelism, which is it's really highly performant, well-supported, and widely used model for systems of accelerators. So, for example, in JAX and the XLA world, it's really the dominant model. So the first step to do this is to introduce. So, okay, how are we going to do this? Well, we have to at some point connect what we do with devices, or maybe some kind of logical abstraction of devices. So this is what meshes. This is the reason. This is the purpose that meshes serve. So meshes are a logical organization of devices as ND arrays. So, for example, you can have lots and lots of different hierarchies. For example, on the left, you see for example, a hierarchy where you have two servers, each of them having 4 GPUs. On the right-hand side, maybe you see a 2x4 grid of accelerator devices. And meshes allow you to view these things as maybe a 2x4 array of devices. So in PartIR, what we do is we don't talk about devices in PartIR, but we talk about meshes as basically a sequence of named dimensions, batch 2 and model 4 in this case. So what happens is that the PartIR iteration loops and the reduction loops always have an associated mesh axis with them. So you say tile on a dimension D, but please use this axis, or sum, but please use this specific axis. So there are a few well-formless constraints for this. We cannot double nest the same axis. So you cannot say tile of axis batch and then tile again of axis batch. And the range value, the range type value, this K that you see there, must be equal to the corresponding axis size. So in other words, we severely restrict the kind of loops that we can write in this language. So this has several consequences. Most of them are good. Some of them are kind of maybe bad and unexplored, but most of them are good. So the consequences are that the device assignment problem becomes trivial, really, because each loop comes already annotated with a mesh axis. So all you have to decide is you have to decide when you're introducing a loop, which axis should I use? Should I use batch or model, for example? And also, it imposes a strong prior or structure, if you want, in the search phase, because the rewrites are not going to need to introduce entirely arbitrarily sized and wildly nested loops. So only loops associated with one of few axes, and the nesting depth only up to the mesh rank. So 2 really makes the search independent of the number of actual available devices. If you have 1,000 devices, you could, of course, try to create arbitrary loops, and then just try to map each iteration of a loop on one of 1,000 devices, and making that work for a really large program would be pretty complicated. But now you only really have to decide. This only really depends on the rank of the mesh. So if you have a mesh of rank 1 containing 1,000 devices, the problem is pretty simple from a search perspective. But of course, we may lose. We don't know exactly what we are losing in terms of performance. Okay, so here's an example of just, I think this is just to show you how it looks in actual code here. So we see a tile expression on the upper left. We have tiled a loop. So this is MLIR notation. So it's SSA form where you can see the region accepting a %R argument, and it has a body that ends with a PartIR yield. And then we apply an action which says tile argument W on dimension 1 and axis shard. And then please propagate the consequences. This is infer propagate tactic. And what you get is you get a loop nest where you see a tile on the outside and a sum on the inside. And yeah, that's the program. That's the program you get. So you get these programs that contain loop nests. So I will. Yes, I have a few slides to talk to you about how do we lower this to SPMD. So I'm going to talk to you a little bit about the SPMD dialect without too many details. So PartIR SPMD is an IR that's suitable as a target for lowering PartIR. It has distributed types that express replication or distribution, explicit redistribution commands. It has reduction instructions along given mesh access. So no devices. Still we're operating with mesh access. In fact, devices get bound really late, like almost at the runtime level. And explicit SPMD ops consisting of base dialect computations, so non-distributed computations. So I think what I have planned to do is just give you a small illustration of the lowering of these concepts through the lowering of a small program. So it may work, it may not work out. Let's see how it's going to be. So if we see here's a program on the top. X is of has some array type, ordinary array type. Y has some ordinary array type, and we see tiling where inside we do a matrix multiplication of slices of X and Y. So this would be your your ordinary, let's say, matrix multiplication. You would want this to be distributed on slices of X, really. So what are we going to do here? The very first thing we're going to do here is we're going to lower this kind of naively, very naively. We're going to look at whatever free variables are inside this tile loop, and we're just going to leave. Just going to lift them out of the closure, and we're going to say, and we're going to introduce explicit commands that distribute these tensors to what we call distributed tensor type, which in this case is going to be fully replicated. So the type that you see there, distributed tensor with x-axis and 8 by 16, denotes a fully distributed tensor that should live on all of the devices. And the second thing we do is we lift x and y like this, and then we lower the tile op to an explicit SPMD op that accepts these distributed tensors now, y1 and x1, and a closure which accepts the local chunk sizes of this, which we call xarg and yarg. And then inside, the body hasn't changed really, so we still do a matmul of the slice of x, etc., etc. And then we give it a distributed type that's called stacked distributed type that really says, oh, all I'm doing here is I'm just going to give you chunks of size 16 by 16. And then we have some kind of retyping information that gives it a proper distributed type, which you see with %2. %2 really folds the stacked dimension into the first dimension of the distributed array and gives you a 32 with braces 0. That means it's actually sharded on dimension on axis x-axis, which is the 0th one. And finally, we do an undistribute. So we take a very compositional form to lowering, which is lift all variables out of the closure, give them distributed types, lower the tile ops, the loop nests to SPMD ops, and finally do some administrative things to give them the right distributed types again. The interesting bit happens next, which is we observe here on the upper left that the argument x is actually sliced inside the body, but it's actually coming from a fully replicated tensor on the outside. So we can realize at this point that we'd be much better off if we were to create a distributed tensor, a sharded tensor for X to start with, and then not have to pass the full tensor to the SPMD computation, just pass the local slice. So we replace the original distribute command, which created a fully replicated tensor, with one that gives you a distributed tensor. And we eliminate the slice from inside the SPMD op. This has the advantage that every device now gets only a local chunk of that tensor and can calculate something. So this is really, these two are the key steps to lowering. Now, lowering step number one, explicitly lift all variables, create distribute ops. Step number two, optimize distribution based on what exactly happens in the body of these SPMD ops. So I realize this is really skimming the surface of it. But for translating summations, we introduce similar SPMD ops, but an explicit reduction command. We have fusion of distribution operators, like, for example, if we undistribute and distribute command, it's equivalent to X, or if we distribute and if we undistribute and then distribute, we can create a redistribute command. So we have several flavors of these things. So I'm just gonna quickly skim over some of. So this is all I had about PartIR SPMD. All I could fit in this seminar about PartIR SPMD. But I'm going to spend a couple of slides about the search design and some initial results we have. So the search design, as I said, it has three components. Rewrite actions. These are the ones that I explained. Basically, just dump dialing, really. Rules that propagate these actions, the propagation rules that I described, and fusion. And finally, we have cost models, which are based on memory and runtime estimation, depending on the users. Usually we use the runtime estimation. But sometimes we just use a memory model, purely peak liveness-based peak memory model. So the key insights is that the users decide on the mesh in advance. So we don't search over possible shapes of meshes. That's coming in. And then we also try to mimic human expert partitioning by propagating argument decisions. So basically, again, we don't try to partition every single op, insert dump dialing ops for every single op in a program. What we do is we say, okay, how would an ordinary programmer start with? They would start with by trying to partition a specific very big parameter, and they would see what consequences that would have. And then they would try to partition something else, or maybe retract. So we do the same kind of stuff. We expose a work list populated by these kind of decisions that a human would take as well. And this is the work list over which our search agents are searching. So we have implemented I realized I didn't say, we have implemented Monte Carlo tree search on top of this game, really. And for transformers, for example, we can achieve within a few episodes, we can achieve what is considered human expert, the best human expert strategy, which is a Megatron paper published by NVIDIA, I think, a few years ago. So that's kind of very promising. And interestingly, we can do this with even if it has 1 layer or 24 layers. There, the things are a little bit trickier, because if it has 24 layers, certainly it has many more parameters. Occasionally, what happens is that there is some shared computation across the layers that allows propagation to work across layers. Or, what is more robust, we have an analysis. So we have an API that allows the users of our system at the JAX level to specify the regular structure of a model. So if you have like 24 layers, but they're all the same layer, and you need to take the same decisions for every layer, through this API, you can avoid exposing all of the decisions to the agent, but rather performing the same decisions for each layer based on what you have decided for one layer. And that, the graph that you see on the right, shows you that if you do not do this, and you do not have any of these shared constants or computations to propagate dependencies, then you never reach the human expert performance for the 24-layer transformer. However, if you do add this argument grouping, you do reach quite quickly. Search time. So the search time scales a little bit with model size. So, you know, as kind of unsurprisingly, and we have ongoing work to speed up step time. Basically we have multi-threaded search for our basically our kind of a workstation, let's say, model, but we also have an entirely cloud-based search as well. And we also have the ability to have some APIs where we are able to cache search results. So if a researcher wants to restart, let's say, from an existing partition model, they can pick it up from a cache and use it in the next experiment. So at the moment, the search is slow. One key limiting factor is that rewriting is expensive, and basically we're trying to speed that up a little bit. But you know, manipulating programs of 50,000 or 100,000 ops and rewriting them is something that is going to be somewhat expensive. So okay, recap. We have a functioning JAX API. We are reaching expected performance on a variety of models. We have some early integration of this API with some pilot users, but it's not yet battle tested. And the user hints on model structure are probably required to reach good performance. This may become better as we improve the efficiency of our search, but at the moment, that's the case. And there are some missing features. For example, we don't yet support control flow. That's in the workings. And there's a small a workshop paper that describes a few more details about the MCTS search. And it's Michael from our team is going to give a talk in the NeurIPS ML for Systems workshop next week. Right, so what's next in conclusions? It's a very active area of work in our team. Lots of stuff to do in terms of IR, improving the search, improving the parallelism we support, improving APIs. I'm not going to go through them in detail. So I think that's my last slide. We need abstractions for partitioning that are platform independent and flexible, and we believe that with PartIR, we follow a principled step-by-step kind of approach. So with small rewrite rules, semantics preserving steps, the program makes sense in all steps of transformation. And it's also a nice workbench to explore program transformation through search, or constraint solving either, or super optimization, or you name your favorite technique. Cool. That's it. I'll be happy to take questions. Thank you.